Hello everyone, welcome to my YouTube channel The Luminous Science. In the previous video, we had studied about the definition of aromaticity along with the aromatic nature of some non-benzenoid compounds. Here we are going to see the aromaticity of benzenoid compounds. So let us see what does benzenoid aromatic compound mean. These are compounds which contain one or more benzene. They are classified into two types. So, benzenoid aromatic compounds are nothing but the compound which contain one or more benzene rings, and they are classified into two types. First one is isolated benzenoid compounds and the second one is fused benzenoid aromatic compound. Isolated benzenoid aromatic compounds, these are the compounds which contain one or more benzene rings joined together by a carbon-carbon bond or carbon bonds. So, for example, biphenyl and diphenyl methane. Here we can see there are two benzene rings which are joined by a carbon bond which is present in that benzene ring only. This compound is called as biphenyl, and here also we can see there is a methane group present between these two benzene rings which are bound together by a carbon bond. This compound is named as diphenyl methane. So here the benzene rings are bound together by a carbon bond, and such compounds are called as isolated benzenoid compounds. Next one is fused benzenoid aromatic compounds. These are the compounds where two or more benzene rings are fused together. As we had seen in isolated benzenoid compound, the benzene rings were bound by a carbon bond, but here in fused benzenoid aromatic compounds there is no such carbon bonds, but the benzene rings are fused. For example, naphthalene and anthrolene. So this is what fused benzenoid aromatic compound and isolated benzenoid aromatic compound mean. The next one is mesoionic compound, a five-membered heterocycle compound which cannot be satisfactorily represented by any covalent or dipole structure but only as a hybrid of polar structure. Such compounds are called as mesoionic compounds. So these are usually a five-membered compounds which cannot be satisfactorily represented by any of the covalent or dipole structure, but they can be represented as a polar structure. As we know, polar is nothing but the poles or charges, that is positive and negative. So these compounds cannot be represented by a covalent bond or dipole structure but can be represented as a polar structure. Like for example of Sidnon. Here we can see a positive charge and a negative charge which is seen on both the oxygen atom present. Here negative is due to the loss of electron, and here the positive is due to the excess of bond or excess of electron present, and the resonance structure can be written as follows. Since there are pi electrons present in this compound, delocalization of pi electrons will take place, and thus these resonating structures can be obtained for the compound Sidnon. So such compounds are called as mesoionic compound. Now let us study few properties of Sidnon. Sidnon or the mesoionic aromatic heterocycle in which the positive and negative charge are delocalized throughout the ring and cannot be represented by a single classical Lewis structure. Lewis structure is nothing but the dipole structure, and as mentioned earlier, this negative and positive charge will be delocalized throughout the ring. And here are some properties of Sidnon. Sidnon is aromatic due to delocalization of pi electron. It is highly stable because of the resonance, and resonance is because of delocalization of pi electron. And Sidnon possesses a permanent dipole moment. The dipole moment is because of the both positive and negative charge which is present in the molecule. And Sidnon can undergo electrophilic and nucleophilic substitution reaction. An application of Sidnons, it is used as intermediate in organic synthesis, important in medicinal chemistry, and some Sidnon derivatives exhibit anti-inflammatory, antimicrobial, anti-cancer activities and analgesic activities. Now let us see what are alternate and non-alternate hydrocarbons. alternate hydrocarbon, linear conjugated chains and cyclic conjugated molecule containing one ring with even number of carbon atom belong to a type of molecule called as alternate. So here mainly we'll consider linear and also the chains and cyclic conjugated molecule which contains even number of carbon atom. So the hydrocarbons which is either linear or cyclic in nature and most importantly contains even number of carbon atom are called as alternate hydrocarbons. In the alternate system, the carbon atom are divided into two classes or set. One set of carbon atom are starred carbon atom and the other set is called as starred carbon atom. These starred and unstarred carbon atom names are given so that the naming or the positioning of carbon atoms become easier. So here in this compound we can see, and also in benzene also we can see there are starred and there are even number of carbon atoms, and each carbon atom which is attached to the doubly bonded carbon atom are starred. So if starred is bound to unsaturated, then it is called as alternate. This will deal with some example in further sessions. And there are types which comes under this. The first one is even alternate hydrocarbon. These contain even number of conjugated atom. In even alternate hydrocarbon, the number of starred and unstarred atoms are equal. Since we are considering the even number of conjugation, thus the number of starred and unstarred carbon atom will be equal. Like for example in 1,3-butadiene, 1,3-butadiene we can see there are two starred and two unstarred carbon atoms. And also when we see benzene also there are three starred and three unstarred alternate carbon atoms, and thus they come under even alternate hydrocarbons. Now let us see the energy level diagram of the even alternate hydrocarbon. As we know, even alternate hydrocarbon contain equal number of bonding and anti-bonding level. The pi electrons are filled in the bonding level. Pi electrons are uniformly spread over the unsaturated, starred and unstarred atoms. So if we consider 1,3-butadiene, there are 4 carbon atoms and 2 double bond. Since 2 double bond, which is nothing but 4 electrons, and each electron, when we consider electron in the conjugated system or delocalization, we usually call them as pi electrons. So here the pi electrons are usually filled to the bonding level. Since there are 4 electrons, the 4 electrons are filled in the bonding level of the energy level. 1,3-butadiene even alternate contain 2 double bond with 4 pi electron which are filled in the 2 bonding level, that is Xi1 and Xi2, and 2 anti-bonding levels are unoccupied. And also 1,3,5 hexatriene is also an even alternate which contain 3 bonding named as Xi1, Xi2 and Xi3, and 3 anti-bonding Xi1 star, Xi2 star and Xi3 star. Here 3 bonding levels are filled by the 6 electrons. The energy level diagram of 1,3,5 hexatriene is similar to that of the 1,3-butadiene. Here we are representing the energy level as Xi1 and Xi2, but whereas for 1,3,5 hexatriene we write another energy level, that is Xi3. And here also we'll add one more energy level, that is Xi3 star. And thus as the conjugation or energy level increases, the Xi numbers can be added as shown. The next type of classification is odd alternate. Those hydrocarbons in which odd number of conjugated atoms are present. They have unequal starred and unstarred atoms. So as the name itself represents, odd alternate, which means that there are odd number of carbon atoms which are conjugated. And here we can see unequal number of starred and unstarred carbon atoms. Like for example in benzyl anion, here we can see there are 7 carbon atoms and there are 4 carbon atoms which are starred and 3 carbon atoms are unstarred. And similar to that, allyl cation, here we can see there are 3 carbon atoms, but only 2 carbon atoms are formed and are starred, and 1 carbon atom is not starred. Now, if we see at the energy level diagram for the odd alternate, these hydrocarbon contain equal number of bonding and anti-bonding level, and also have non-bonding level with the energy level 0. Like for example of allyl cation, as we know the energy level diagram which was shown for the alternate hydrocarbon, the number of bonding and anti-bonding orbitals will always remains the same. But in odd alternate, we can also see a non-bonding energy level which lies exactly between the bonding and the anti-bonding energy levels. Usually, the non-bonding energy level will always be 0. So, this is the energy level diagram for an odd alternate. Allyl cation, which contains one double bond with the 2 pi electrons. So, the double bond can be seen here, 2 pi electrons which are filled in the bonding level. So, those 2 electrons are filled in the bonding level. Whereas for the allyl radical, which contains 3 electrons, that is 2 from double bond and 1 from the anion, out of which 2 are filled in the bonding level and 1 is filled in the non-bonding level. The next one is non-alternate hydrocarbon, the conjugated atoms with the even or odd carbon atom. The carbon atom are divided into two sets, that is starred and unstarred. Here starred carbon atom is linked to another starred carbon atom. So in non-alternate hydrocarbon for a cyclic system, it must contain at least one odd membered cyclic system. So as here mentioned, non-alternate hydrocarbon, that means the carbon atoms which is present in the compound are not starred alternatively, or the number of starred and unstarred will not be same. Thus, the condition is that there should be presence of at least one odd membered cyclic system. So here we can see it is a 5-membered ring, and here 3 starred carbon atoms are present and 2 unstarred carbon atom present. And one more point to be noted is the starred carbon atom is linked to starred carbon atom. So one starred carbon atom will be linked with another starred carbon atom. So since this system can be either odd or even, if it is an even system then or odd system, in both the cases there might be possibilities that there might be bond between the starred carbon atoms, or maybe there may be presence of alternate starred carbon atoms. So this is all about the non-alternate hydrocarbon, the property of aromaticity of benzenoid aromatic compounds, their classification. If you have liked it, please share, like and subscribe my YouTube channel, The Luminous Science. See you all in the next video with a new topic.